Welcome back to the bench. If you are listening to this right now, you aren't here for a basic foundational introduction to electronics.
No, definitely not.
You are an experienced professional. You're a stakeholder in high reliability systems or an advanced avionics technician. You already know what a resistor, an inductor, and a capacitor do when they're just, sitting by themselves on a breadboard.
Right. We're
Yeah.
assuming a high baseline here.
Exactly. So our mission today is to rapidly rebuild your advanced comprehension of alternating current networks. We are moving far past those pedagogical textbook abstractions you might have learned years ago.
The 101 level stuff.
Right. We're going to deconstruct the quantum, the electromagnetic, and the actual diagnostic realities of parallel RLC networks and resonance.
Specifically focusing on how they operate within the incredibly unforgiving environment of aerospace systems.
And just to set the stage, the architectural framework and the really deep research fuel driving our conversation today, all of that is drawn directly from the recently declassified project Ampere Avionics Training Synthesis.
Which is an incredible document.
It really is. So the intention here is to provide you with a high signal-to-noise master refresher.
We want to establish a rigorous, advanced framework right out of the gate.
Yeah. So for our roadmap today, we're going to start by examining the topological axioms and the complex vector mathematics required for this specific circuit analysis.
And from there, we need to transition into the actual subatomic physics of the reactive components. What is physically happening inside the material?
Then we'll take that theoretical resonance and translate it into functional RF tank circuits.
Before finally concluding with severe environmental failure modes and the highly specific bench-level diagnostic protocols, you actually need to isolate faults in these complex systems.
A lot of ground to cover.
It is, but it's essential.
So I want to start with the absolute foundational shift in topological axioms.
The divergent point.
Right. Because when we analyze standard series circuits, the fundamental rule drilled into everyone from day one is that current is the constant. It is the absolute metric across all interconnected components. But the moment we shift to a parallel architecture,
that rule is completely inverted.
it's entirely inverted. In a parallel topology, the electromotive force, the voltage, is what remains the constant parameter across all individual branches.
Regardless of what components are actually in those branches.
Right, and that single topological divergence forces a complete shift in our advanced analysis frameworks.
Think about it. When you are dealing with a series circuit, your primary analytical tool is Kirchhoff's voltage law.
KVL.
Right, KVL. You are looking at voltage drops around a closed loop, usually using mesh analysis. But in a parallel RLC network, because the voltage is the constant, KVL becomes largely useless for finding the dynamic values we actually care about.
You have to transition.
You have to move to Kirchhoff's current law, KCL, and utilize nodal analysis.
Your focus shifts entirely to mapping the vector sum of branch currents interacting at common nodes. Exactly. And that brings up a specific analytical protocol detailed in the source material that, frankly, usually trips people up.
The arbitrary voltage rule.
Yes, the arbitrary voltage rule applied to parallel RLC calculations.
It's a classic stumbling block.
It really is. The protocol states that if the source voltage is unknown in your schematic, you can just assume an arbitrary value.
You literally just pick a number.
Right, say 50 volts. You use that to calculate your relative branch currents and ultimately find your total network impedance. I remember looking at that for the first time and thinking, wait, how can you just fabricate a voltage and expect the physics to work out?
It seems completely counterintuitive until you remember what impedance actually is.
Right.
Network impedance, denoted as Z, is a fixed physical characteristic of that specific circuit at that specific moment in time.
It's baked into the hardware.
Exactly. It's entirely determined by the physical geometry and the material properties of the components.
Yeah.
The internal resistance, the inductance, the capacitance.
And the frequency of the alternating current source.
Yes. But the key is, impedance is completely independent of the applied voltage amplitude.
So whether the generator is pushing 5 volts or 500 volts, the physical restriction to the alternating current remains exactly the same.
Correct. The ratio of voltage to current, which is the literal definition of impedance, remains constant.
Okay.
By assuming an arbitrary voltage, you are simply giving yourself a mathematical baseline to calculate the individual branch currents.
Because you need those branch currents to find the total current vector.
Right. And once you have that total current vector, you apply Ohm's law for AC circuits.
Yeah.
You take your arbitrary voltage, divide by your calculated total current, and the arbitrary voltage effectively factors itself right out of the final equation.
Leaving you with the exact impedance profile of that network.
Exactly. It's an elegant workaround.
But getting to that total current vector, that's where the math has to reflect the physical reality of alternating current.
We have to move entirely away from simple algebraic addition.
Right, because in a DC circuit, if branch A draws 2 amps and branch B draws 3 amps, your power supply needs to provide 5 amps.
Simple arithmetic.
But when we are dealing with root mean square, or RMS, values across reactive branches in an AC circuit, we are forced into strict geometric vector addition.
You absolutely cannot just add an inductive current to a resistive current algebraically.
Because they aren't happening at the same time.
Precisely. The currents are peaking at different moments in the AC cycle.
They are out of phase.
Because they are out of phase with one another, adding them algebraically would be like trying to calculate your total distance from home by adding miles driven north directly to miles driven east.
You can't just add the numbers. You have to draw a map and find the hypotenuse.
That is exactly what vector addition is doing.
Let's walk through that map for calculating the total line current. First, you have to find the net reactive current. You have the inductive branch and the capacitive branch.
The inductive current dictates the primary vertical axis direction on our theoretical map.
So we subtract the capacitive current from the inductive current to find the net reactive current.
And the result of that specific subtraction tells you whether the overall circuit behaves inductively or capacitively. But it is critical to remember this dynamic. In a parallel circuit, because voltage is constant across all branches, the branch with the lowest reactance will draw the highest current.
Therefore, the component with the lowest ohm value will dominate the net reactive profile of the circuit.
Exactly.
Once you have that net reactive current, that vertical line on our map, you calculate the total circuit current using the Pythagorean theorem.
You take the resistive current, square it, add it to the net reactive current squared, and take the square root of the whole thing.
The total current is the hypotenuse of that triangle.
And that vector mathematics is the only way to accurately model the reality of what's happening inside the wires.
The problem is that foundation-level training often obscures why these components behave the way they do.
They get treated like black boxes.
Right. Current goes in, phase shift comes out. But if you are troubleshooting a flight-critical system or trying to understand why a specific filter is failing at 40,000 feet, you need to understand the atomic and field-level mechanics that actually cause these specific phase shifts.
You have to know the physics.
I want to look at exactly that.
Yeah.
Let's move beyond the mathematical pedagogy and dive into the quantum and electromagnetic reality of reactance.
Let's do it.
Let's start with capacitance at the atomic level. In military specification aviation components, we are frequently dealing with dielectrics made of tantalum pentoxide.
A very specific, very robust material.
What is physically happening inside that specific material when an alternating electromotive force is applied across it?
To understand that, you have to look at the molecular structure. Tantalum pentoxide is formed through an electrochemical anodization process.
It creates a highly stable insulating lattice.
Right. When you apply a voltage potential across that lattice, you induce dielectric polarization. The material contains covalently bonded molecules that act as electric dipoles.
They act like microscopic magnets, but for electric charge.
Essentially, yes. As the voltage potential rises on one plate, the electron clouds of these atoms literally distort. They stretch.
The negatively charged electron clouds are pulled toward the positive potential.
While the heavy, positively charged nuclei are pushed toward the negative potential.
But the electrons don't break free and flow, right? Because that would be a short circuit.
Exactly. They just stretch. And that physical subatomic charge displacement is what creates an internal electrostatic field.
And that electrostatic field stores potential energy.
It does.
But here is the critical intuition behind the phase shift. We always hear the phrase, current leads voltage by 90 degrees in a capacitor.
It's a mantra at this point.
But why 90 degrees? Why not 45 or 180? It comes down to the relationship between the rate of change of the voltage and the stretching of those electron clouds.
Yes. Current, by definition, is the rate of charge accumulation. So think about an AC voltage waveform as a sine wave.
Okay, picturing it.
When that voltage waveform is crossing the 0-volt line, it is moving from negative to positive.
Well, positive to negative.
Right. At that exact moment, crossing 0, The curve is at its steepest. Its rate of change is at its absolute maximum.
The voltage is mathematically zero, but it is changing faster than at any other point in the cycle.
Exactly. And because the voltage is changing so rapidly, the rate at which those electron clouds are stretching, the rate of charge displacement, is also maximized.
Therefore, the current flow is at its mathematical peak, while the voltage is at zero.
Yes. Now, as the voltage waveform continues up and reaches its maximum peak, the curve momentarily flattens out before coming back down.
At the very top of the wave.
At that peak, the rate of change is zero, the electron clouds are fully stretched, and for a microsecond, they are totally stationary.
Because they are stationary, the rate of charge displacement is zero, meaning the current drops to zero.
Yes. This derivative relationship, where current is proportional to the rate of change of voltage, translates in physical reality to an exact 90-degree leading phase shift.
The current peaks a quarter of a cycle before the voltage peaks.
Exactly.
Okay, so if the capacitor is acting like a stretched rubber band storing energy in an electrostatic field, what is the inductor doing on the other side of that parallel loop?
A very different process.
Inductance is governed by Faraday's law and Lenz's law. How does simply coiling a copper wire create an opposing 90-degree phase shift?
It comes down to the interaction between current and magnetic fields. As alternating current flows through the conductive windings of an inductor, it generates a magnetic flux.
And because the AC source is constantly altering the magnitude and direction of the current, that magnetic field is never static.
Right. It is constantly expanding out from the wire and then collapsing back in, physically cutting across the adjacent windings of the coil.
And Faraday's law dictates that any time a conductor is exposed to a changing magnetic field, an electromotive force, a voltage, is induced within that conductor.
Yes, and then Lenz's law adds the critical twist.
The counter EMF.
Right. That induced voltage will inherently oppose the changing current that created it. It is a counter-electromotive force.
It is nature's way of resisting a change in momentum. The induced voltage fights the source voltage.
Precisely.
So applying the same rate of change logic we used for the capacitor, how does this opposing voltage create a 90-degree lag?
Again, look at the AC sine wave, but this time for the current.
Okay.
When the AC current is crossing zero, its rate of change is at its maximum. Because the current is changing so rapidly, the magnetic field is expanding or collapsing at its maximum velocity.
Therefore, the induced opposing voltage, that counter EMF, is at its absolute peak.
So when the source is trying its hardest to push current through the zero crossing, the inductor pushes back with maximum force.
That makes perfect sense.
This massive opposing voltage effectively delays the current waveform from rising. It acts as a physical brake.
By the time the current finally reaches its peak, its rate of change flattens out to zero.
The magnetic field stops moving for a microsecond. Because the field isn't changing, the opposing voltage drops to zero.
And this dynamic delay mathematically and physically results in the current lagging the applied voltage by a quarter cycle.
Or exactly 90 degrees.
I want to take those two distinct realities, the 90-degree leading capacitive current driven by electron cloud distortion and the 90-degree lagging inductive current driven by magnetic opposition, and put them together.
Now we're getting into the engine.
We need to look at the tank circuit engine, the actual phenomenon of parallel resonance. First, we have to define the state of equilibrium.
Resonant frequency.
Yes. Resonant frequency is the specific, mathematically precise frequency where the inductive reactance and the capacitive reactance are perfectly equal.
Which is dictated by the physical properties of the components.
But the real magic happens when you look at the branch currents at that specific resonant frequency.
Because the capacitive reactance and inductive reactance are equal, and because they are in parallel across a constant voltage, their respective branch currents are forced to be equal in magnitude.
But their phase angles are completely opposite.
Exactly. One is peaking 90 degrees ahead of the voltage, and the other is peaking 90 degrees behind it.
Relative to each other, they are exactly 180 degrees out of phase.
And this is where we apply Kirchhoff's current law at the primary circuit node where those branches meet.
The nodal analysis we talked about earlier?
Right. If you have two currents of equal magnitude entering a node, but they are exactly 180 degrees out of phase, their vector sum is zero.
They perfectly cancel each other out from the perspective of the external power source.
Exactly.
Wait, let me stop you there. This is a concept that constantly trips up technicians on the bench.
It's a conceptual leap.
If the internal current between the capacitor and inductor at resonance is massive, How is the external current dropping to a minimum? How is the main generation bus not seeing this massive current draw?
Because the energy is trapped within the parallel loop.
It's isolated.
It is a closed cyclical transfer. Think about what is actually happening internally. The capacitor has energy stored in its electrostatic field.
Right.
As that field collapses, it drives current into the inductor. The inductor uses that energy to build its magnetic field.
And then the cycle reverses.
When the magnetic field collapses, it acts as a generator, driving the current back into the capacitor, recharging the electrostatic field with the opposite polarity.
It is the electrical equivalent of a heavy mechanical flywheel spinning with massive momentum.
That is a perfect analogy.
Once you get that heavy steel wheel up to speed, it contains a massive amount of kinetic energy. The internal forces are huge.
But the motor driving the flywheel, the external power source, only needs to provide tiny little taps of energy to overcome friction and keep it spinning.
At resonance, the external line current drawn from the generator drops to its absolute minimum.
The external power source only needs to supply enough current to overcome the tiny parasitic resistances in the component materials.
The DC resistance of the copper wire.
And the dielectric losses in the capacitor. The reactive currents themselves are self-sustaining.
To model this precision in advanced aerospace engineering, we have to move into a different mathematical framework. Complex admittance.
Denoted by Y.
Right, and measured in Siemens. It is the reciprocal of impedance, measuring how easily a circuit allows current to flow, rather than how much it restricts it.
It gives us a much cleaner framework for parallel nodal analysis. Admittance equals conductance, which is the real part, plus imaginary susceptance.
And susceptance is the reciprocal of reactance.
In a parallel network, the total susceptance is the algebraic sum of the capacitive and inductive susceptances.
But remember, at the exact point of resonance, those two values are equal and opposite.
So they cancel each other out, forcing the imaginary susceptance term to perfectly zero.
If the imaginary part of the equation drops to zero, the network admittance is reduced entirely to its real conductance.
And since impedance is the reciprocal of admittance, what happens to the total impedance of the tank circuit at resonance?
It becomes purely resistive, and it becomes massive, theoretically infinite, though the parasitic resistance keeps it finite.
This massive spike in impedance at one specific frequency is what gives the tank circuit its entire purpose: selectivity.
The ability to act as a filter.
And that selectivity is governed by the quality factor, or Q.
The Q factor is the ratio of reactive power to average real power dissipated.
It quantifies the efficiency of the energy storage versus the energy loss per oscillation cycle. For a parallel RLC network, a higher parallel resistance minimizes the damping effect on the circulating currents,
yielding a higher Q factor.
Exactly.
And a high Q factor is what gives you a remarkably narrow bandwidth. Bandwidth equals the resonant frequency divided by the Q factor.
That math is critical.
I want to put this into a practical, real-world aerospace application so we can visualize it. Let's look at an aircraft's VHF receiver front end governed by ATA Chapter 23 for communications.
A classic application.
Civil aviation voice communication operates on an amplitude-modulated spectrum with channel spacing that can be incredibly narrow. We are talking about isolating signals within an 8.33 kilohertz window.
Think about the physical environment that receiver is operating in.
It's hostile.
You have an aircraft on approach trying to capture a microvolt level signal from air traffic control at exactly 121.5 megahertz.
The signal is incredibly weak.
At the exact same time, the aircraft might be flying directly over a high-power commercial FM broadcast tower.
Transmitting at 107 megahertz with tens of thousands of watts of power.
Without a highly selective filter, that massive 107 megahertz signal would completely overwhelm the antenna, bleed into the circuitry, and completely saturate the receiver's low-noise amplifier.
The ATC signal would be obliterated.
Exactly. This is where the parallel LC tank circuit acts as the ultimate gatekeeper.
In this application, the tank circuit is placed in a parallel or shunt configuration relative to the main signal path coming from the antenna.
At 121.5 megahertz, which is the exact frequency it is tuned to resonate at, its internal impedance becomes massive.
It acts like a high-impedance brick wall.
The 121.5 megahertz ATC signal hits that wall, cannot pass through the parallel branch to ground, and is forced to continue down the primary signal path into the receiver.
But look at how it treats the interfering signal.
For that 107 megahertz FM broadcast, the tank circuit is far off its resonant frequency.
Because it is not resonating, its total impedance is incredibly low.
It acts as a near short circuit.
The massive, unwanted 107 megahertz signal hits that low impedance path and is harmlessly shunted directly to the airframe ground.
Completely bypassing the sensitive receiver stages.
It is elegant physics. But for this filter to maintain that level of geometric precision, isolating a microvolt signal within an 8.33 kilohertz window while flying through turbulent air, the physical characteristics of the inductor and capacitor must remain absolutely stable.
And in an aircraft environment, stability is the ultimate challenge. The vibration, the thermal shock, the atmosphere pressure changes, all of these forces are actively trying to physically alter the components and detune the circuit.
Which perfectly transitions our discussion into component intelligence and surviving the extremes of DO-160G environmental standards.
We are moving away from theoretical math and into the brutal physical reality of hardware.
Commercial off-the-shelf, or COTS, parts simply cannot survive this environment.
They completely lack the electromechanical resilience.
If you put a commercial capacitor in an unpressurized avionics bay, it will fail.
Quickly.
In these flight-critical networks, we rely on specific MIL-SPEC or JTX equivalent component families. I want to look closely at the wet tantalum capacitors.
Specifically the MIL-PRF 39006 family.
Yes, the construction of a wet tantalum is an absolute engineering marvel designed specifically for extreme durability and stability.
It utilizes a sintered tantalum pellet as the anode.
Sintering is a process where fine tantalum powder is pressed and baked at high heat,
fusing the particles together but leaving a highly porous, sponge-like structure.
This provides a massive internal surface area for charge storage within a very small footprint.
And the dielectric is that tantalum pentoxide layer we discussed earlier, grown directly onto the complex surface of that pellet.
But the critical feature that gives it the wet designation is the liquid sulfuric acid electrolyte.
Right. The liquid electrolyte permeates the porous pellet, acting as the true cathode connection to the dielectric layer.
All of this is contained within a hermetically sealed tubular metal case.
Usually with a specialized elastomer seal backed by a laser-welded glass-to-metal seal to prevent the acid from leaking.
That sulfuric acid electrolyte is what allows the component to operate across an extreme thermal profile.
From a cold soak of negative 55 degrees Celsius up to a scorching positive 125 degrees Celsius.
However, there is a critical engineering rule when operating these at the upper thermal limits: voltage detrating.
This is non-negotiable.
If the ambient temperature in an avionics bay exceeds positive 85 degrees Celsius, the technician or engineer must derate the applied voltage by a factor of 2/3 of the rated voltage.
This is where theory meets consequence.
Yes.
If that derating protocol is ignored during the design phase, or if a thermal management system fails and the bay overheats while the capacitor is under full voltage, you trigger the primary failure mode.
The combination of high heat and high electrical stress causes an immediate breakdown of the tantalum pentoxide lattice.
The insulation fails.
Exactly. When the insulation fails, direct current flows through the liquid electrolyte.
This high current causes localized boiling of the sulfuric acid.
The electrolyte outgasses, creating massive internal pressure.
That pressure builds until it violently ruptures the hermetic seal.
The highly corrosive electrolyte leaks onto the circuit board, eating through traces.
And the capacitor itself becomes a catastrophic short circuit across the parallel network.
Now let's contrast that failure mode with the RF inductors, governed by MIL-PRF 15305.
These are physically very different structures.
They are typically constructed with a phenolic, iron, or ferrite core wrapped in fine, heavy-gauge copper winding.
And entirely encapsulated in transfer-molded epoxy.
They are designed to withstand 100 grams of mechanical shock and severe random vibration, but they have their own specific Achilles heel.
Thermal cycling. Thermal cycling is what attacks the inductor over time.
When an aircraft takes off from a runway in the Middle East at 45 degrees Celsius and climbs to 40,000 feet where the ambient temperature is minus 50 degrees Celsius, every component physically shrinks.
When it lands, it expands.
The epoxy encapsulation, the ferrite core, and the copper wire all have different coefficients of thermal expansion.
They expand and contract at completely different rates.
That differential expansion places immense tensile stress on the fine copper wire winding buried inside the epoxy.
Over thousands of flight hours, this constant stretching and compressing can physically fatigue and fracture the wire.
When that wire snaps, you have an open circuit.
Alternatively, Excessive DC current flowing through the coil can saturate the magnetic domains within the ferrite core,
This drastically alters the inductive reactance parameters.
effectively detuning the tank circuit without physically breaking it.
And we have to address the massive shift in how these components are packaged and mounted because it has introduced entirely new failure modes.
The shift to surface mount.
Right. If you look at legacy architectures, the VHF tuners in a Boeing 737 Classic or a DC-3, they relied heavily on axial leaded through-hole components.
They had long, flexible wire leads that passed through holes in the circuit board,
Those wire legs acted like shock absorbers.
flexing to absorb vibrational energy and thermal expansion.
But modern line replaceable units, or LRUs, like the Garmin G1000 glass cockpit suite or the flight control computers on a 787, have transitioned almost entirely to surface mount devices, or SMDs.
The components are microscopic and they do not have wire leads.
This transition introduces a severe vulnerability to thermomechanical shear forces.
SMDs are soldered flat, directly to the surface of the rigid printed circuit board.
When the aircraft undergoes that rapid temperature cycling, descending from a sub-zero cruising altitude to a hot desert runway, the FR4 fiberglass circuit board and the ceramic component expand at completely different rates.
Because there are no flexible wire leads to absorb that movement, the dimensional change places massive shear stress directly on the microscopic solder joints holding the component to the board,
It is literally trying to rip the component off the pads.
which is exactly why avionics technicians must strictly adhere to the IPC JSTD001 Class 3 standards.
This is the absolute highest reliability standard globally for soldered electrical assemblies.
It mandates perfect intermetallic solder fillets to guarantee physical retention against those shear forces.
For a through-hole component, that standard dictates a minimum of 330 degrees of circumferential wetting around the plated through-hole on the primary solder side.
Wetting refers to the capillary adhesion of the molten solder to the base metal.
If a technician leaves a void, or if the solder only flows around 200 degrees of that pin, it is a structural compromise.
It might pass an electrical continuity test on the bench, sure.
But under the constant high-frequency vibration of a jet engine, that weakened joint will inevitably fracture and fail.
This brings us to a crucial operational skill for anyone maintaining these systems.
Advanced diagnostics and signal tracing protocols.
Before a technician can even touch a soldering iron to fix a broken joint, they have to interpret the schematic to isolate the fault.
And in aviation, because these aircraft and their subsystems are manufactured globally, schematic symbology is an absolute minefield.
It is a trap that catches inexperienced technicians constantly,
You have to know the origin of the LRU you are diagnosing.
because you will constantly jump between the American National Standards Institute, NSI IE 315, and the European International Electrotechnical Commission, IEC 6061 unseen standards.
I actually saw this exact symbology trap play out on a bench test for a 737 transponder a few years ago.
Oh, this happens all the time.
The shop was under a time crunch, trying to get a grounded aircraft back in the air. A junior tech grabbed the schematic, which was drawn to IEC standards.
Okay.
He was looking for an inductor in the circuit path. Under the American ANSI standards, an inductor looks like a series of scalloped loops emulating a coiled wire. It is very intuitive.
But under the European IEC standard, an inductor is drawn as a solid, filled rectangle.
Right. And the IEC standard for a standard resistor is a hollow rectangle.
I see where this is going.
So this tech looked at the schematic, saw a solid rectangle, and in his rush, his brain registered it as a resistor.
Fatal mistake.
He hooked up his digital multimeter, put it in resistance mode, and probed across the component. It read 0.1 ohms.
Because a DMM is only measuring the DC resistance of the copper wire making up the coil, it is not measuring the inductive reactance.
Exactly. But because he thought it was a resistor, he assumed a 0.1 ohm reading meant the component had suffered a catastrophic internal short circuit.
He spent 3 hours trying to isolate a cascade fault that didn't exist.
Preparing to pull chips off the board simply because he didn't realize he was looking at a perfectly healthy inductor.
This is why a standard DMM is largely useless for advanced AC diagnostics on reactive networks.
It tells you absolutely nothing about the inductive reactance, the capacitance, or the quality factor of the circuit at its operating frequency.
To see the true dynamic response, you must transition to a dynamic bench setup.
You need an environment like the NITO 130ST trainer bridge to a digital storage oscilloscope, or DSO.
Let's walk through that live bench diagnostic protocol. I want you to visualize the screen.
How do you definitively prove that a parallel RLC network is resonating correctly?
You begin by configuring an arbitrary waveform generator, an AWG, to output a clean 10-volt peak-to-peak sine wave.
You calculate the theoretical resonant frequency of the tank circuit you were testing based on the component values, and you set the AWG exactly to that frequency.
Next, you connect channel 1 of the DSO in parallel across the AW output.
This establishes your input voltage phase reference. You need to see exactly what the power source is doing.
Here is the crucial step. You cannot measure current directly with a standard oscilloscope probe.
You have to measure voltage drop.
So you insert a precision, low-inductance 1-ohm current-sensing resistor in series with the main feed line providing power to the parallel network.
You map channel 2 of your oscilloscope across this 1-ohm resistor.
Because of Ohm's law, voltage equals current times resistance.
If the resistance is exactly 1, the voltage drop across it gives you a direct one-to-one mapping of the total line current waveform.
Now you look at the screen. When you engage the system at that calculated resonant frequency, what must you see to prove the circuit is functional?
First, you look at the phase relationship.
You must observe the voltage waveform on channel 1 and the line current waveform on channel 2 perfectly in phase.
They must cross the zero line at the exact same moment. The phase shift must be exactly 0 degrees.
And second, you look at the amplitude.
The amplitude of the current waveform on channel 2 must dip to its absolute minimum as you tune the frequency precisely to resonance.
Those two visual confirmations, zero phase shift and minimum line current amplitude, prove definitively that the internal reactive branch currents are perfectly balanced.
The 90-degree leading current is perfectly canceling the 90-degree lagging current.
And the circuit is presenting maximum impedance as a purely resistive load.
Let's stress test that theory with some fault isolation scenarios. Let's translate this textbook theory into the kind of diagnostic logic you would see on an NCT AET examination, or more importantly, on the hangar floor.
Okay.
Scenario A. You are diagnosing a VHF receiver's front-end filter. The tank circuit is supposed to be isolating the carrier wave, but the inductor's fine copper winding has suffered one of those thermal shear fractures we talked about.
The wire is broken.
It is an open circuit. What is the immediate electrical consequence?
The parallel architecture is instantly destroyed. From an electrical perspective, the inductor no longer exists.
The circuit effectively degenerates into a single series capacitive pathway connected straight to ground.
And what does a capacitor do at high VHF frequencies?
Capacitive reactance is inversely proportional to frequency. At high frequencies, the reactance is exceptionally low.
So the total network impedance plummets.
Instead of acting as a high-impedance brick wall to block the desired signal and force it into the receiver, it acts as a wide-open drain.
The desired ATC signal, along with broadband RF interference from every other transmitter in the area, will flood right past the filter.
Flow through the capacitor to ground.
And completely bypass or saturate the mixer stage of the receiver. The radio goes deaf.
Let's look at scenario B. This one is about environmental degradation detuning a healthy circuit.
A very real-world problem.
A parallel RLC circuit is operating perfectly at resonance, doing its job. The aircraft climbs to 40,000 feet, and the ambient temperature in the unpressurized radome drops to minus 50 degrees Celsius.
This extreme cold soak causes the dielectric material inside the capacitor to physically contract,
shrinking its capacitance value by 10%. What is the immediate effect on the total line current you would see if you had an oscilloscope hooked up to the generator feed?
If the physical capacitance drops, the capacitive reactance increases. They are inversely related.
This immediately breaks the resonant equilibrium where inductive reactance equaled capacitive reactance.
So the 180-degree cancellation effect is lost.
The net reactive current circulating in the tank is no longer zero. Because the capacitive reactance is higher, it draws less current.
Meaning the inductive branch now dominates. The circuit becomes net inductive.
And because the reactive currents are no longer perfectly canceling each other out, what happens to the math?
The vector sum of the total line current must mathematically increase.
The external power source suddenly has to supply more current to feed that uncanceled reactance.
So as the temperature drops and physically detunes the capacitor, you will see the total line current amplitude rise in the scope.
And the current waveform will begin to shift, lagging behind the voltage waveform because the inductive nature is taking over.
That concept of uncanceled reactance drawing extra current brings us perfectly to the real-world implications of power factor.
Power factor is the ratio of true power, which is the power doing actual work, to apparent power, which is the total power the generator has to supply.
In these parallel networks, it is calculated as the resistive current divided by the total circuit current.
At perfect resonance, the power factor is 1.0.
But if a tank circuit is detuned, or if you have a massive array of parallel inductive loads on an aircraft, like heavy flat motors, fuel pumps, and actuators,
Your total current vector stretches out, your power factor drops.
let's say an aircraft system has a degraded power factor of 0.80. Why is this a severe danger to the aircraft's ATA-24 electrical power generation bus?
A low power factor means you have a high amount of uncanceled reactance in the system.
This uncanceled reactance draws what we call blind or reactive current.
This apparent power performs absolutely no mechanical work. It doesn't turn a motor, it doesn't process a signal, it doesn't heat a probe.
However, it is real physical current flowing through the copper wires.
The alternator physically has to push those electrons.
Yes, it occupies valuable generation capacity from the engine-driven alternators.
And more critically, as that blind current flows through the wiring harnesses, the contactors, and the generator stators, it generates destructive thermal loads.
We call them I²R losses. Power dissipated as heat equals the current squared times the resistance of the wire.
Because current is squared in the formula, even a moderate increase in blind current creates a massive increase in heat.
You are physically heating up the aircraft's power grid, degrading the insulation on the wires, and stressing the generators, all for absolutely zero functional return.
This is why power factor correction is so critical in heavy systems. It is not just a math problem, it is a thermal management problem.
Now that we have mapped the component behavior, the diagnostic protocols, and the systemic impact, I want to pivot to the final section of our outline.
Niche intelligence and the invisible aerospace threats.
The deployment of these complex RLC networks at 40,000 feet or in low Earth orbit for satellite systems subjects them to supply chain and environmental vulnerabilities that are entirely absent in consumer electronics.
I want to start with radiation hardening.
When an airframe is operating at cruising altitude in the stratosphere, or a satellite is in orbit, it is no longer protected by the dense lower atmosphere.
It is constantly bombarded by galactic cosmic rays, high-energy protons, and solar flare radiation.
We established earlier that inductors are essentially macroscopic coils of copper wire and iron or ferrite cores.
Because of their sheer physical mass and lack of delicate semiconductor junctions, they are inherently immune to ionizing radiation.
But capacitors are a completely different story. They are exceptionally vulnerable to total ionizing dose, or TID, degradation.
What actually happens when a radiation particle hits a capacitor?
When a high-energy photon or particle strikes the tantalum pentoxide dielectric layer, it transfers its kinetic energy to the atomic structure,
It physically strips electrons out of their covalent bonds in the atomic lattice.
creating what we call electron-hole pairs. In a normal environment, these pairs might recombine.
But in the vacuum of space, or under the continuous bombardment at altitude, these displaced charges become permanently trapped within the dielectric material.
And that trapped charge fundamentally degrades the core function of the dielectric,
Right.
its ability to insulate.
As more and more radiation damage accumulates over the lifespan of the airframe, the insulation resistance drops.
This leads to a steady, permanent increase in direct current leakage.
The capacitor slowly begins to act more like a resistor, allowing DC current to bleed through the tank circuit.
This is exactly why those military-grade wet tantalums, the MIL-PRF 39006 family, are mandated for these environments.
They possess extreme radiation tolerance compared to solid, dry capacitors.
Exhaustive aerospace testing, bombarding these components with 20 mega-electron-volt photon beams up to 4.5 kilograms of cumulative exposure, has proven their resilience.
Under that intense cosmic bombardment, these wet tantalums maintain their direct current leakage well within a 125% increase margin,
They degrade, yes, but they do not fail completely.
ensuring the resonant tank circuits remain functional for the lifespan of the vehicle.
Another catastrophic threat, but this one born from well-intentioned environmental regulation, is the RoHS dilemma and the phenomenon of tin whiskers.
In the early 2000s, the restriction of hazardous substances mandate forced the global commercial electronics industry to remove lead from their solder manufacturing processes.
They transitioned almost entirely to pure tin alloys.
But pure tin behaves in a highly unstable manner when exposed to the extreme environments of aerospace.
What does pure tin actually do when subjected to the compressive stress and aggressive thermal cycling we discussed earlier?
It creates a solid-state extrusion. Pure tin plating, under the compressive stress of a component lead being soldered to a rigid circuit board, will spontaneously erupt.
It extrudes microscopic, hair-like conductive crystalline structures known as tin whiskers.
This isn't melting or electromigration. It is a physical extrusion from the crystal lattice of the metal itself to relieve stress.
And these aren't just tiny bumps. In an unpressurized avionics bay undergoing rapid thermal cycling, these whiskers can grow at an alarming rate.
They can reach several millimeters in length.
And they are highly conductive. A famous historical example of this occurred in 1998 with the Galaxy V telecommunications satellite.
The primary control processor failed due to a short circuit caused by a tin whisker.
It knocked out pager and credit card processing systems across North America.
When these whiskers grow long enough, they bridge the microscopic gap to adjacent component pads, causing catastrophic, intermittent short circuits across parallel networks.
They can handle enough current to send a false signal to a flight control computer before vaporizing like a fuse.
Making the fault nearly impossible to trace on the bench because the evidence literally destroys itself.
Because of this catastrophic risk, the aerospace, defense, and medical device sectors fought aggressively for, and won, strict exemptions allowing the continued use of tin lead or SNPB solder.
Lead acts as a stabilizing agent in the alloy, suppressing the crystalline grain structure that causes whisker growth.
But because the global supply chain is flooded with pure tin commercial parts, technicians have to utilize aggressive mitigation strategies.
They have to perform hot solder lipping. Physically dunking the component leads in molten leaded solder to dissolve and replace the pure tin.
Followed by the heavy application of polyurethane conformal coatings over the entire board to physically smother and suppress any potential whisker growth that might still occur.
Which leads directly to our final existential threat to these systems, supply chain integrity and the AS6081 standard.
We are currently dealing with a massive diminishing manufacturing sources and material shortages crisis in aerospace.
Often abbreviated as DMSMS. Think about the life cycle mismatch.
A commercial airframe like a 777 or a B-52 bomber might remain in active service for 30 to 50 years.
But the production life cycle of a specialized RF inductor or a specific high-reliability capacitor might only be 5 to 7 years before the original manufacturer obsoletes it.
So an airline needs a replacement board for a 20-year-old navigation system, but the components haven't been manufactured in a decade.
This forces procurement departments to hunt for parts in the gray market, dealing with unauthorized independent distributors.
And this is exactly where the counterfeiters are waiting.
The sophistication of these counterfeiting operations is staggering. They aren't just printing fake labels.
They harvest ancient, thermally degraded circuit boards from electronic waste dumps.
They physically strip the old passive components off the boards with heat guns.
They replate the oxidized leads to make them look shiny.
Then they perform a process called blacktopping. They chemically strip or sand off the old manufacturer markings and re-stamp them with fresh, highly desirable MIL-SPEC beat codes and part numbers.
They sell exhausted, thermally degraded, unreliable junk back into the supply chain as brand new, high-reliability components.
If one of those black-topped capacitors makes it into a flight-critical parallel resonant filter, its internal dielectric is likely already compromised.
It will fail under thermal stress.
To combat this, technicians and quality assurance engineers must be intimately aware of the defense mechanisms outlined in the AS681 standard.
You can no longer just look at a part and trust a paper certificate of conformance.
The industry relies heavily on destructive physical analysis and advanced metallurgy. One key protocol is decapsulation.
Quality engineers use fuming nitric or sulfuric acid to carefully eat away the epoxy or plastic casing of a sample batch of components.
To physically verify the internal die structure and the wire bonding geometry against the original manufacturer's specifications.
They also rely heavily on X-ray fluorescence, or XRF, testing.
XRF involves bombarding the component leads with high-energy X-rays. This causes the metal atoms in the plating to emit secondary X-rays that carry an exact elemental signature.
An XRF scan can verify the exact metallurgical composition of the plating, ensuring it contains the required lead content for aerospace use.
And proving it hasn't been quietly replated with cheap, whisker-prone pure tin by a counterfeiter in a back alley.
It requires a forensic level of attention to detail to keep these networks functional.
Synthesizing everything we have explored today, mastering the vector mathematics of alternating current, visualizing the subatomic electron cloud distortions in a dielectric, and anticipating the catastrophic realities of DO-160G environmental extremes.
All of this directly translates into your ability to isolate incredibly complex faults.
Whether you are probing a cell-cal decoder that refuses to trigger or a VHF tuner pulling in broadband static, the foundational reality of the circuit is governed by the delicate equilibrium of the parallel tank circuit.
The formulas are just tools. True diagnostic power comes from moving past textbook memorization and understanding the underlying physics driving the component behavior.
When you understand how a changing magnetic field fights a stretching electric dipole, you elevate your troubleshooting logic from mere guesswork to precision engineering.
Absolutely.
I want to leave you with a final provocative thought to mull over as you head back to the bench.
Okay.
We have spent this entire deep dive establishing how these passive physical components, coils of copper wrapped around ferrite, plates of tantalum suspended in acid, rely on absolute physical geometry and material purity to maintain electrical resonance.
They are inherently physical devices.
But as we look toward the next generation of aerospace engineering, specifically hypersonic flight and advanced stealth platforms, we are seeing the inevitable shift toward completely optical, photonics-based avionics computing.
Light instead of electricity.
Exactly. If signal processing transitions entirely to manipulating photons through fiber optics rather than pushing electrons through copper, how will that redefine the concept of frequency filtering?
Will the physical electromagnetic tank circuit we've relied on for a century be completely rendered obsolete by optical resonance rings?
Something to consider as you review your next schematic. Thank you for taking this deep dive with us today. Keep questioning the fundamentals, and we will see you next time.